talk. And Jeff Kuhn is from UBC, Vector Institute, and DeepMind. Correct me if I'm wrong, Jeff.
That's correct.
Okay. And yeah, today you'll give us a talk about open-ended quality diversity and AI-generating algorithms in the era of foundational models. And yeah, let's welcome Jeff. Also, it's 7:30 for him in Vancouver, so like he woke up super early to give us this talk.
Yeah, so I'm going to be sipping some coffee while we talk. So it'll be a proper tea talk. Well, at least coffee talk. All right, should I take it away?
Yeah, the floor is yours now, Jeff. Oh,
Okay.
actually, wait, sorry, just one more question. Do you want to take questions during the talk or like in the end of the talk?
I'm happy to take questions, especially if they're clarifying questions. If it's more a discussion type question, maybe that's better for the end. But if there's something that you don't understand and it's going to, I'd like you to build on a solid foundation of knowledge.
Okay, sounds good. So yeah, people online, if you have clarification questions, you can just raise your hand. And when the time is right, either me or Jeff will let you ask your question.
Yeah, I can't see raised hands with the way that I shared my screen. So you'll have to just jump in and let me know there's a question.
Okay, then I'll do this. And then if we have discussion questions, let's keep them until the end of the tea talk. All right, the floor is yours, Jeff.
Sounds good. Well, hello, everybody. Thank you. It's great to be here. I'm still waking up and clearing my voice, so I'm sorry for that. So today I wanted to try to do a few different things. I want to first kind of motivate these things called quality diversity algorithms, open-ended algorithms, and AI-generating algorithms that my colleagues and I have been working on for a while. Sorry about my voice. And then I wanted to discuss new possibilities that have been unlocked with respect to these algorithms in terms of foundation models. So like many things, foundation models are opening up a lot of new frontiers, and that applies to these algorithms as well. And so I'm going to spend the back half of the talk kind of telling you about kind of all this new possibilities that have been opened up with foundation models. Before I begin, though, I want to talk about AI safety. So this is like a super important topic to me, one that I've been thinking about and talking about for almost, 15 years now. I take it extremely seriously, and I encourage you to as well. I had a paper with Joshua and Jeff Hinton and Daniel Kahneman and many others in Science where we kind of make the case that this is something we should take very, very seriously. Also, there are some unique safety issues for the kind of work that I'm going to be talking about today, and I've written some articles with some great colleagues specifically on those topics. I encourage you to check those out as well. So we must proceed really cautiously and wisely and prioritize safety as we do this kind of work. This talk is not focusing on safety. That requires its own focus. So I'm not going to go deeply into these topics, but I just want you to know from the get-go that I think about them a lot, including in the context of the work that I'm going to present today. All right, so putting that aside, there's a paradox in life that I want to start with, which is that if you try too hard to solve a really ambitious problem, you will fail. Ironically, if you ignore the objective entirely, you're much more likely to succeed. So as a metaphor for that, imagine that you're an agent in this little maze here, and you're incentivized to only go north. Well, if you do that, that's what happens here. You go north and you just kind of pound your head against the wall forever. And every time you make progress on the path towards success, we disincentivize you. And we say, no, you're supposed to get closer to the goal. And we kind of tell you to go back over here. And you get stuck pounding your head against this wall forever. In contrast, if we just incentivize an algorithm to go to new places, do something novel, then you'll explore this maze and trivially solve it. Now, you might think that that is an overly simplified problem that doesn't show up in the real world, but in fact, that is one of the dominant ways that the world operates when we're trying to do complex, hard things. So for example, this shows up all the time in the history of science and technological progress. If you went back to the time of cooking over a campfire and you said, hey, I will only fund scientists in my queendom that give me more cooking for less, faster cooking, less smoke, you would never invent the modern microwave, because to invent the microwave, you had to have been working on radar technology and noticed that a chocolate bar melted in your pocket. Similarly, if you went back to the time of the abacus and you said, I will only fund scientists that give me more flops per second, you would never invent the modern computer, because to do that, you had to have been working on vacuum tubes and electricity, which were technologies that were not invented because they help in terms of computation. And I really want you to think about that. Almost every major technological breakthrough, the stepping stones that led to it, did not measurably help you accomplish that goal. And so the conjecture here is that the only way to solve really hard problems may be to create problems as you go and not try to keep the final goal in sight as you try to accomplish that goal. So this leads us to this concept of goal switching, which is that when you're trying to solve task A, if you make progress on some other task, that it could be important and you should start practicing that other task also. Imagine you're a roboticist and you're trying to get bipedal locomotion and you're measuring progress as forward speed. Well, if you start seeing a robot crawl on 4 legs or balance on 1 leg, don't throw that out because it does not measurably improve your progress towards forward, your forward speed. Instead, what you'd like your algorithm to do is say, oh, that's an interesting thing to be working on. Maybe I should practice balancing on 1 leg because that might ultimately be a stepping stone towards bipedal locomotion. And so we want our algorithms to kind of have that feeling of capturing serendipity in the lab, saying, oh, that's interesting, let's try to do that, or that, I didn't expect that, I wonder if we can do a little bit more of that. And so that brings us to this kind of this family of algorithms called quality diversity algorithms, which my colleagues and I have been working on now for over a decade. And the idea here is that we want to produce a diverse set of high-performing agents or policies, much like evolution produced all of the diverse but yet really impressive things you see on the right here. And the poster child algorithm for quality diversity algorithms is this algorithm called MapElites, which was invented by my colleague Jean-Baptiste Moret and I exactly a decade ago. And I want to show you exactly how this algorithm works because this is effectively the playbook that we're going to adopt time and time again in all of the work I'm going to show you in the rest of the talk. So MapElites says, here's what we're going to do. I want to produce something like a fast-moving robot. So I have some performance criterion. Well, what I'm going to do is I'm going to pick dimensions of variation I care about in the space, like height and weight. I'll discretize the space, and then I'll run this simple loop. I will parameterize. I have a parameter vector that describes my search space. So first, let me evaluate a random parameter vector. I'll figure out its height and its weight and its performance, which I'm visualizing here in color. And then we'll put it in the cell in that grid where it belongs, according to its properties in the diversity dimensions. And then if it's, well, then I'll run this loop. I'll take something out of the archive. I'm going to call that archive a stepping stone, solutions that I've found so far. Take something out of the archive, change it a little bit, reevaluate it, figure out where does it go now in the archive. And here's the thing, if it's the best thing I've ever seen at that location in the archive, then I'll swap it in and keep it. So I end up with a map, which is all the best things I've found at all the different points in this map. But the map is defined by dimensions of diversity. And the best thing I've found according to the performance criteria is what I keep there. And I can just run that loop forever. And so this ends up producing not a single best solution that I have found, like the single best Go player in self-play, but instead I get this huge diversity of different types of solutions that are different yet high performing for that type of thing. And I get basically a surface of solutions. And that teaches me a lot about my search space. Rather than one randomly high-performing thing, I learn, oh, there are peaks and valleys in my search space. I can do well here and here, but not over here. And so, for example, when we first invented this algorithm, a year before I had done this work on soft robots, which at the time was going viral on YouTube. And this soft robotics work had produced this kind of parade of fun, quirky, different creatures that looked interestingly diverse, and they were. But there's a cheat to this video, and that is that every one of these robots came from a different run of optimization. That was really what was the fuel providing diversity. Within each run, you got minor variants on each one of these creatures. And so I said, hey, can we run this new diversity generating algorithm to try to produce lots of diversity within one run of the algorithm? Like evolution within one run produced jaguars, hawks, and the human mind. And so if you run classic optimization in this problem, you get very low performing solutions. They're all kind of black, and they don't explore the space very much. If you specifically encourage diversity in these two dimensions, while also optimizing for performance in like a Pareto dominant multi-objective optimization algorithm, if you know what that is, you get higher performance, you get yellow, but look how little it performs the search space, even though it's explicitly being encouraged to do that. And then if you run map elites, you get a complete sea change. For the same amount of compute, look at the difference you got in terms of exploring that search space. It's just night and day, which is pretty cool. And you learn about there's different local optima, etc. Also, you can go into these algorithms and do science to look at like what happened over the course of innovation. And what you find is that for any final champion within the map, you can go back and look at the history of kind of where did the curriculum take it through space to ultimately have it land at that point. And you see these long circuitous paths through the search space. You would never have known to end up here, the best thing to do is do this particular walk through the search space. And so that's really going to prove critical to this work. So we took the ideas of map elites and we used them for this paper in Nature in 2015, where we're trying to produce rapid adaptation. And so if you can actually see the map on the floor of Nature in simulation ahead of time, you figure out all these diverse, high quality, different ways to walk as a robot. And then once the real robot becomes damaged, you can search through that basically that archive of high performing yet diverse gates to find a gate that still works despite the damage. And that produced adaptation in about 6 to 12 experiments in about 2 minutes on a real robot. We also use the same ideas for this Go Explore algorithm, which you may have heard of, done by these wonderful people. And the idea here is that for many hard exploration problems in reinforcement learning, these are problems that are hard because you have to take many, many, many actions before you get any reward. And so you're not getting a lot of signal from the environment. Go Explore basically says, hey, we want to learn the highest quality way to get to as many different states as possible. So you get quality and diversity. And this algorithm just blew the roof off of hard exploration challenges in the Atari benchmark. The grand challenge at the time was this game Montezuma's Revenge, and you can see this graveyard of attempts to try to do well on this game on the bottom here, and then you can see Go Explore basically just completely changed the game here, literally, and ultimately beat the human world record and produced superhuman performance on this game. It went on to beat the entire Atari benchmark. It was the first algorithm to do that, with some caveats that you can see in the paper, and it does really well on robotics tasks. So even intrinsically motivated PPO, which is state-of-the-art still RL, is orange here. It does terrible on these tasks where you only get a point if you put up your toys away, whereas Go Explore solved it every single time. So I hope I've convinced you that quality diversity algorithms are interesting. They produce a diverse set of high-performing agents. They harness goal switching within the algorithm. They do these weird, curricula where you don't know where you're headed, but ultimately you get to really high places. But what's missing? Well, they're still stuck in a single environment. Traditionally in ML, we pick an environment like Go, and then we just work on it a long time. And then once we solve that, then we pick the next environment. But that's not what we want. What we really want are these things called open-ended algorithms, which I have dedicated my whole career to. I've been working on this for about 20 years, and I hope to work on it for the rest of my career. What we want in open-ended algorithms are algorithms that will truly endlessly innovate. And I mean endlessly. I mean, if we ran them for a really, really long time, no matter what, every time we gave them another month of compute, they would surprise us again. So there are examples, there are exactly 2 examples we know of in the universe of open-ended algorithms. One of them is natural evolution. It's been running for 3.5 billion years. It produced all of the amazing things you see on the right here and below, and it continues to surprise us, as we saw with the COVID pandemic. Another example is human culture. It doesn't end. Science doesn't end. It continues to innovate, and every time it does, it solves one problem that just opens up new opportunities to go learn and solve new things. So, as my friend Jean-Baptiste Mouret put it, could we create an algorithm that was worth running for 1 billion years, where you'd want to come back and check on it the 1,000,000th and first year because it's still delighting and surprising and innovating? So one of the key ingredients, I think, for algorithms like this is that, oh, you have a question?
Sorry, yeah, I think there is a question online from Gregory. Maybe I can read it for you. It was about the map. Does map elite depend on specific interpretability regarding representation, like on the fact we understand the phenotypical elite can be useful, mutated in a way that preserves the strength with high probability?
Yeah, good question. So in some problems, you can just hand pick your dimensions of variation, and therefore they're interpretable, like height and weight. Or if you're using a neural net policy to solve Montezuma's revenge, it could be like, I don't know, a number of different keys that it has, or a number of different rooms that it gets to. You can also use latent representations that are learned within deep neural nets. So you could take a parameter vector that has some, I don't know, like 512 dimensions, and you could consider each of those 512 dimensions to be a dimension of the map. Then you've lost interpretability, because obviously deep neural nets learn their own representations of the world, and you don't know what that 12th neuron is doing. You can do other techniques like ask an LLM to pick a couple dimensions of variation, and maybe even score something along dimensions, and it's semi-interpretable because you picked them and they're semantically meaningful, but it's up to the LLM to kind of do a good job of faithfully judging things along that dimension, and that won't work perfectly. So there's lots of options in terms of how you deal with that. All right, I'll press on. Let me know if there's follow-up questions there. That's a good question. Well, we'll see some examples of us playing with those ideas later in the talk. Okay, so I think probably the key ingredient to open-ended algorithms is that every time they solve a problem, that unlocks and opens up new opportunities, new problems, new learning environments. For example, evolution produced the challenge, if you will, the learning opportunity of leaves high up in trees. And then the solution to that problem in the form of giraffes and caterpillars that eat those leaves. But then giraffes and caterpillars are new opportunities for things to eat them, live inside them, cooperate with them, etc. And so you want a thing that invents problems as it goes. And so I'll just throw it out there. I think that creating open-ended algorithms is one of the grand challenges in computer science. I think there's a Turing Award out there for whoever can figure it out. And so it's a pretty exciting thing to work on. So one of our most, I can't call it recent anymore, it's 6 years old, but a major attempt that we made to push towards open-ended algorithms is this thing called POET. The idea in POET is to endlessly generate increasingly complex and diverse learning environments and their solutions all in one run. And so the way that POET works is this. We're going to parameterize the environment, which at that point was novel, and then we're going to periodically generate new learning environments, and we're going to have a population, an archive of different environments, and we'll add something to this archive by pulling out an environment, changing a little bit, and adding it back to the archive if that environment is not too easy and not too hard for the current set of agents in the population, and also if it's novel, it's different from any of the environments we've seen so far. Then we're simultaneously, for each environment, going to have a paired solution that's optimizing to try to learn and solve it. And we'll allow the solutions to jump from niche to niche. If you suddenly make an innovation in one environment that makes you better on another environment, will allow you to go and invade that other niche and take over and become the agent paired with that environment. So that will allow goal switching and all the magical ingredients of open-endedness. So all of the environments you see here were automatically generated by the system itself. And it starts simple. It has little tiny stumps, little tiny gaps, maybe some rugged terrain. And then later it starts to combine these challenges and produce big gaps, big jumps, etc. And so therefore, the system is automatically picking problems and trying to solve them. Now, you can do science on this, which is pretty cool. For every single environment that you see in blue here that POET created and solved, you can go back and you can say, hey, can I use the exact same learning algorithm that produced a solution to that environment, but just directly try to solve that environment? And it turns out in every single case you fail because you needed the curriculum of POET to kind of work yourself up to being able to solve that environment. And now you might say that's cheating, curriculums, we know curriculums help. You can even create basically a hand-designed curriculum that tries to go from a simple environment to a hard environment for that particular environment, and in every case that fails as well. You really need these weird counterintuitive paths through the search space to solve these environments. So here's one of my favorite plots in my entire scientific career. I've been trying to produce this for 15 years now, and it's basically a phylogenetic tree of environments. And so what you get is it kind of invents different styles of environments, and then it kind of it riffs on that theme for a long time, kind of like evolution produced, you know, the great cats and reptiles and aquatic creatures, and then it kind of riffs on that theme, and you get these huge diverse lineages and species, different types of things, and a lot of exploration within that type of thing for a very long time. So to conclude POET, I think it shows the benefits of QD and generating challenges while you solve them. However, it too is still kind of trapped now in a narrow distribution of tasks rather than a hand-chosen task. And we want to break through from that. So we'll return to that in a second. I want to take a step back now and think about the real grand ambition of our field. So if you think we should make AGI or ASI, and that emphasis on the if, that's a separate conversation, I still think we've got a ways to go. And the question is, how will we get there? And I think there's a clear trend in machine learning that I've observed in my career, which is that hand-designed features basically always get replaced by learned, hand-designed pipelines, I should say, always get replaced by learned pipelines as you get more compute and data. We've seen that for all of the things in this bulleted list, and you can probably imagine many others. This is kind of like the bitter lesson from Rich Sutton. And that suggests an alternate path to producing extremely powerful AI. And that is, let's not try to hand design it. Let's just learn it using compute. So we're going to use lots of pre-training, lots of search, but ultimately produce something that is very, very sample efficient. And there's an existence proof of that, which is you. Congratulations, you're the smartest thing we know of in the universe. But it took a planet-sized computer and 3.5 billion years of experimentation to ultimately find you. And so we could do the same thing with a lot of compute. If we want to make progress on this, which I call AI generating algorithms, using AI to generate better AI, we need to make progress on 3 pillars. You need to meta-learn the architectures, the learning algorithms, and automatically generate effective learning environments. And so handcrafting each of these is very slow. It's limited by our own intelligence and creativity or lack thereof. It's better just to kind of create the right search algorithms and let machine learning do the heavy lifting. So far I've spent a lot of time on pillar 3, trying to figure out how are we going to generate these learning environments. And so that's where we are so far in the talk. I've kind of now explained QD algorithms, open-ended algorithms, and AI generating algorithms. And so for the rest of the talk, as I promised, I want to talk about this new era we're in, the era of foundation models, and how that has kind of really changed the game for these types of algorithms. So I want to start with work that came out of my lab here at UBC called OMNI, which stands for Open-endedness via Models of Human Notions of Interestingness, led by Jenny Zhang. And I really think OMNI is an important breakthrough for the field. So let's begin talking about it. To create a truly open-ended algorithm, we need a vast environment search space or task space. So something really, really, truly vast. However, obviously, once you have a truly vast search space, then now you end up with a needle in a haystack problem, because most of the tasks in that search space are going to be impossible, nonsensical, too hard, or too easy. So this is really like a needle in a haystack problem. How can we find tasks that are learnable and interestingly new? So to figure out whether or not something is learnable, we have pretty good methods. My team at OpenAI produced one that we're going to use in this thing, which is basically like, have I gotten, has my rate of success improvement, is that kind of a healthy rate of improvement every time I try to train on something? The real problem here is that how do you figure out what counts as an interestingly new task to learn on? And that's shown by the following. It's really easy to have kind of infinite learning progress, to always be able to learn without that learning being interesting learning. For example, I could generate some really big, long random number string, and then I could always just ask you to memorize 10 more digits of it, and 10 more digits and 10 more digits. So there's always some more learning for you to do on this problem, infinite learning progress, but it's completely useless. Why do you want to memorize random digits? And so this happens all the time in reinforcement learning. We come up with these intrinsically motivated challenges, or we say, hey, why don't you go try to find new states or produce new body configurations for the robot? And we hope that will then cause the agent to go and kind of explore the world. But in truth, you end up with all these pathologies. Every time we try to quantify what counts as a a proxy for interestingness, if you optimize against that measure, you end up with pathologies like a robot just staring at a TV tuned to a dead channel because that's infinitely new states, or a robot just switching on the ground because that's an infinite number of robot positions. So this gets back to what Justice Potter Stewart said, which is that there are things in the world that we don't know how to define, but we know them when we see them. So how do we get that the human sense of interestingness into our algorithms? Well, it turns out that an answer kind of magically showed up in the last few years, which is that foundation models exist and they have a knowledge of what is interesting. They've read the entire internet, and including lots of humans complaining about what they find boring, and like a couple of them mentioning what they find interesting. And so basically foundation models have distilled this ineffable concept of interestingness into their weights. And now we can just ask foundation models, hey, I've already done these 12 problems. I'm pretty good at them. Here's a proposal for a 13th problem. Is that problem interesting given what I've already done before? So that brings us to OMNI, which is open-endedness via models of human notions of interestingness. And the idea here is we're going to use learning progress to measure whether a task has high learning progress using the method I mentioned from my team at OpenAI. But the new part is that we're going to ask foundation models to judge before we start training on a task, whether that task is an interesting task to be training on. And then we'll have an RL agent try to train on all of the tasks the system thinks we should be training on. And so we tried this on Crafter and Baby AI. In both cases, if you uniformly sample tasks, you do terribly because there's too many tasks and you end up working on uninteresting tasks. If you only focus on tasks for which you have high learning progress, you do pretty well. But you do even better if you also add a filter for tasks that are interesting to work on. Now, you might ask, what are we judging on? And the answer is, ahead of time for this environment, we hand chose, actually the people who made these tasks hand chose kind of what counts as a number of tasks that are worth training on, that are worth learning. But we let our system pick any tasks, and it ends up doing well on these things that ahead of time people said are the interesting things to do in that environment, which is kind of what you want. You could imagine that for any domain. However, those domains had only a small set of possible things to do. We really wanted to push the boundaries here and say, can we really operate in an infinite task space where you're not limited ahead of time? So we picked this kitchen environment, and in here there's like an infinite number of things you could do. We specifically allow any task specifiable in words, in English words. So you could like put the toaster under the sink and put a plant down there too, could be one task. Now, a problem is once you allow any possible task, you need what I call a universal reward function, which is you need to be able to judge whether that any possible task was accomplished or not. So first, we tried video models that could watch a video and tell us if that task had been done. I ultimately think that's the right answer here, but those weren't good enough at the time we did this work. I still don't think they're great, but they're getting better. But another option we realized is that you can just ask GPT to produce a reward function in code. So we allow GPT to spit out code. The code can query the state of the world, like where is the toaster? Is it under the sink? And then it can return whether or not you have accomplished whatever task you set out to. So the system is now going to simultaneously produce both a task description and a reward function for that task in code so that it can check whether or not that task was accomplished. And so now if you do universal sampling, you're totally toast. But also, if you do learning progress, you're also toast. There's just too many possible tasks to train on, and you're not focusing on an interesting subset of tasks. But if you use OMNI, you make steady progress on this held out set of tasks that ahead of time we thought would be interesting things to do in the environment. So you're really gaining skills that align with kind of a human notion of useful skills. And also there's an interesting curriculum in here. It says like, first I'll figure out how to find apples, then I'll figure out how to find and pick up knives, and then I'll figure out how to use a knife to slice an apple. And you can imagine where that would go if you ran it for a really long time. So a pro to OMNI is now we can operate in truly infinite task spaces, but we're still kind of trapped in one environment, this kitchen environment. We really want, to push towards truly open-ended algorithms, which means a truly vast environment search space. So that brings us to this notion, this concept that I proposed in my 2019 AI generating algorithms paper, which is if we want a search space that can express any possible environment, including being as rich as all of the stuff that existed on Earth, we need a kind of a name for that type of environment. And so I thought, what is the most expressive search space imaginable? And I said, well, how about something that could express any computable environment? And I said, I'm going to call that a Darwin complete environment, which is kind of a mashup between being Turing complete and having the richness we saw with Darwinian evolution. And so I'm defining a Darwin complete environment as a search space that allows any computable environment. These could be logic problems, coding problems, problems in any possible simulator, any video game, etc. And when I initially proposed the idea of Darwin completeness, I could only think of one search space that would fit the bill, that would meet that high bar. I'll return to that in a little bit. But recently when I was teaching a class here at UBC, a student said something to me that made me realize there's actually a second one, and that is code. If you're generating problems in code, then that is Turing complete, and therefore that can express any computable environment, and therefore that is Darwin complete. And so that brings us to OMNI, where we said, hey, why don't we pair OMNI with a true Darwin complete search space by allowing the system to write its own code to represent its own learning environment. And it can therefore produce code for anything. And so now we have OMNI produce code that describes learning environments and reward functions. That makes it Darwin complete. And then we're going to have OMNI also judge whether those environments are interesting and have a high learning progress. And so it automatically produces all of the environments you see here. So it produces a little tiny agent that can jump up and down on these little platforms, a ball kicking through posts. It makes the platforms have gaps between them. Then it produces a more complicated obstacle course, knocks down a bunch of dominoes, ends up knocking down a tower of blocks, et cetera, et cetera, et cetera. Now, the reason why all these environments are physically 3D simulated is because we have limited compute. So we asked it to only generate pi-bullet simulator environments. We could have easily also asked it to do logic tests and coding tasks and other simulators, other video games, whatever you want. Now, the slowdown here is that every time we propose an environment, it takes RL very long time to learn that environment. RL is very sample inefficient. So we couldn't run this for very long. And so we said, let's just pretend that the agent, every time we propose an environment, the agent learns it. So we can see kind of like, where does this end up in terms of environment generation? Let's let the environment generator go nuts and like run for a very long time. And you get this kind of phylogenetic tree or graph of environments. And it's really, really cool what happens in here. It starts to create different types of environments. Like, it kicks a ball through goalposts, and then it creates a whole soccer field. Then it creates the challenge of bouncing the ball off a wall through the goalposts, and then bouncing the ball off a wall through moving goalposts. Simultaneously, it's riffing on different themes like exploring a building, cleaning up a cluttered construction site, or cleaning up dishes in a cluttered restaurant. And it just innovates and innovates and innovates forever. And it's really, really exciting to see all the different things that it's proposing. And note that none of these problems are like too weird. They're all kind of like the kind of things that humans might want robots to do, which is a good sign. So OMNI finally allows us to focus on interesting tasks. OMNI Epic allows us to generate any possible environment. So this is one of the first algorithms I've produced in my career that you might want to run for 1 billion years. I don't actually think it would work. I think we'd run into pathologies and it would stall out. But I don't know exactly where those pathologies are. I have some guesses, but I would want to run it for long enough to kind of find out what they are, and then we can fix them and keep going. So we're starting to get the hint of algorithms that might be open-ended, which is pretty cool. We just need more compute. So I mentioned that there were 2 Darwin complete search spaces that I'm aware of. One of them is code. The second one, which I wrote in the original AI generating algorithms paper, is the idea of just have a deep neural net be the environment. So I want to take you back to 2019 when it first occurred to me, hey, why not just have a neural net be the entire environment? You give it an observation, like the current state of the world, and you give it an action, and it just steps forward and returns to you the next frame of the world, complete with, a picture, sound, maybe touch sensations if you have some sort of bodysuit. I thought it was so crazy to propose that it might be a career risk for me to put that in my paper. I'm like, people are going to dismiss you as this is a person who just thinks technology can do everything, AI can do everything, and no one's gonna think that you're a serious person. So I almost didn't put this in the paper, but I couldn't convince myself that it was wrong. It just seemed like this is coming. I don't know exactly how long it's going to take, but it felt right. So I put it in there, took the risk, and but I thought it would be a very, very long time before a neural net might actually just be the entire environment. That was 2019. So exactly what, 6 years later, we put out the Genie project out of DeepMind, which is a world model that can generate any environment. This is just a neural net. You give it a picture, you give it an action, it gives you the next observation from the environment. We just train it on a huge amount of online videos, and you end up being able to ask for any world you want, like generate a clay, an orange clay creature that running around a forest platformer, and it produces a picture for you. You can use like I don't know, like DALL-E 3 for that, and then you give it an action, it steps the environment. You give it an action, it steps the environment. So if you give it the picture on the top right here, and then you can basically take your keyboard and mouse and start to send actions to this thing, and you get to control that little orange blob, and you can see the result in the bottom right here. And so at the time, you just get this like 1 to 2 second clip of this little orange blob kind of blurring out, but you're controlling a picture. Pretty cool. We took my children's art, so my kids had made these pictures here, and then they got to step into the world from their imagination that they had drawn and control the eagles in their drawing, or the football player, etc. So we like to think they were the world's youngest video game designers. And again, look how blurry and short these videos are. You could also use it to do robots, and it would learn how to pick up a bag of potato chips or whatever. And I want you to think about the fact that this is like a new class of foundation model. So they're very general, that you can build on top of them. You can do fine tuning to make them better at a subset of domains. You can do RLHF on them. And we'd even study that scaling laws apply. So the more compute you give them, the better. And so you can extrapolate that that Genie 1 was kind of like the GPT-1 of this foundation world model. And if you give it more compute and more data, we expected better things to come. And lo and behold, that turned out to be true. So I think only like 9 months later, we produced Genie 2, which was effectively the same ideas, just scaled up. And now you're getting more realistic graphics. The videos last longer, and you have less pathologies. Like they kind of stay coherent for longer. And the amount of different worlds that you get to create and operate in is huge. Because it's kind of like GPT, you can ask it about anything. And so now imagine training agents in all of these different environments here and more using a system like OMNI paired with Genie. Like the sky is the limit. Inside of Genie worlds, different actions produce different results. You get different object interactions, like you can blow up this barrel, or you can use your samurai sword to chop this balloon, which seems like a pretty fun thing to do. But then a couple months later, we produced Genie 3. So this is now, I think, like 2 months ago. And look at the fidelity of this thing. It's incredible. It looks like a AAA video game. So here's a helicopter flying around Hawaii. Here's a jet ski flying around, the Festival of Lights, including physical interactions, like beautiful lighting reflections on the water. This is one of my favorites, a firefly flying around this beautiful treehouse world. And I want you to just reflect on the fact that we went from something that was so crazy to think about that I thought it was a career risk to mention in 2019 to barely possible in 2024 to this in 2025. All right. So now imagine Genie 4 or 5 or 10. Like this stuff is going to be extremely powerful, extremely high fidelity, and extremely diverse. And if you could imagine pairing that with something like OMNI, then you could have open-endedness in a Darwin complete search space using either OMNI Epic or foundation world models like Genie. So it's really an exciting time to be an open-endedness researcher, because now we can generate a huge diversity of learning environments customized to the current learning skills of the agent and kind of the desire of which direction if the system finds interesting. All right, so I've focused a lot on pillar 3. I want to get back to pillar 2 here, meta learning algorithms. So my team at OpenAI produced this project called Video Pre-Training. And the idea here is that open-endedness, automatically generated environments forever, if we can just generate those environments, we still have another problem, which I mentioned earlier, which is that learning each next interesting challenge is very, very compute intensive. Exploration is hard, RL is very sample inefficient, and so that is a huge tax on these algorithms, just how slow they are to learn. And so the question is, can we harness pre-training? Just like GPT is really good at many skills, and then you can fine tune it to get a little bit better at coding challenges, can we do the same thing for embodied agents? And so a solution is, like pre-training GPT on text, is can we go pre-training on all the skills people show in online videos? So we chose Minecraft as an example. We're going to allow a computer to, or require a computer to use the same interface humans do, a mouse and keyboard, and try to learn those really complicated things that humans do on computers. In this case, it's video games, but it could have been using, Microsoft Word or whatever. And what we find is, like GPT, scaling laws apply. The more pre-training data you give the system, the better it gets out of the box, zero shot. So here are different amounts of pre-training and different amounts of skills showing up. And it's not until you get to really, really OpenAI level of compute and data that you start to get the system doing interesting things out of the box, including things that take humans about 2 minutes and 2,000 actions, 2,000 to 3,000 actions, which is pretty cool. And I want you to draw your attention. Here are some videos of agents. I want to draw your attention to the rightmost video. So imagine you drop an agent in a new village, okay? This agent, because of pre-training, it doesn't just randomly mash buttons and kind of twitch around in the middle of this thing and hope that it eventually stumbles upon reward. Instead, it knows how to explore, it knows how to behave in this environment. So it systematically explores this village. It knows how to open doors. If it sees a chest, it knows that it should open it. If it sees a flight of stairs, it knows that it should climb it. And this makes you primed and ready to discover rewards in the environment and figure out what it is that the system we're trying to ask it to do. It's therefore much more efficient than just what typically happened before, which is like epsilon greedy exploration for reinforcement learning, which means just kind of randomly pressing buttons and hoping something good happens, which is never going to work in a complicated environment. So pre-training for the win. And we show that. So here is a challenge. Then it was a grand challenge or whatever, an open challenge, I'll say, in reinforcement learning was, could you get an AI agent to get diamond tools in Minecraft? And what we show is that without pre-training, you can't do anything. So if you reward the tasks on the way to diamond tools, without pre-training, you learn none of the intermediate skills. I guess you ultimately learn one. But with pre-training and then a little bit of RL on top of that, you steadily can learn all of the skills that you need to learn to ultimately get diamond tools in Minecraft. This is a skill that took skilled humans 20 minutes and about 24,000 actions on a keyboard and with a mouse. And now we have RL agents just kind of routinely and steadily learning to be human or superhuman on this task. So recently, a team that I'm on at DeepMind produced kind of the next version of this. We are training not just in one environment, but we're training one agent across many different environments, all the environments that you see here. And we end up with an agent that can play a variety of different embodied tasks. And what's really amazing about this agent is that if you train it in 12 environments and then you ask it to zero-shot transfer to the 13th environment, it does almost as well, that's this gap here, as an agent specifically trained in that 13th environment. So you're getting huge amounts of transferable skills as you kind of level up these generally capable agents. And now imagine the Sima agent in a thing like Genie. In fact, you don't have to imagine it. Here is Sima in Genie. So here's an imagined world with 3 different worlds. Zero shot, we ask the Sima agent to go through the left door, go through the center door, or go through the right door. And the Sima agent is able to go and explore this hallucinated world by, I think this was Genie 1 actually, or maybe Genie 2. So you can imagine in Genie 3 and then Genie 10. So to conclude VPT and Sima, pre-training enables us to learn hard exploration tasks much more efficiently. That should greatly catalyze open-ended algorithms like pairing with Genie. All right, now for the remainder of the talk, I want to walk you through a few projects that basically use this same playbook of open-endedness plus foundation models and OMNI to do really powerful stuff. So the first thing I want to show is the ADAS. Oh, do we have a question?
Yeah, sorry. I just thought there have been 2 questions on the chat. Let me read them to you. So the first is from Gregory. Great stuff. For very complex tasks, the subtask partitioning might not be apparent, and so the relevant subtask may not be apparent and hence not selected. This would seem to occur even in the OMNI context. For example, who knew that playing music off CD players would require laser diodes? Even in regular human-driven science, we see papers whose value is not recognized for a long time.
Yeah, exactly. And the key here is that the value is not recognized in terms of its ultimate practical implications. So let's not ask the algorithm to think about ultimate practical implications. Like humans, we valued those original contributions because we thought they were interesting. Some peer reviewers or some grant agency or some scientists thought it was worth working on those because they were interestingly new capabilities or just fun. And so we did develop them, and ultimately we realized we could make them into CD players. So that's what OMNI is trying to do, is to say, let's not think about the overall goal, whatever it is, getting to Mars or making like AGI. Just do interesting stuff, and we'll have a short-term function that says, given everything we've had so far, this next thing that's interesting, that's new, I haven't seen that before, go ahead, build that, train, figure out how to do that. And then if you do, we'll like add that innovation to our growing set of innovations, and then we'll keep going. And OMNI should do that, and it should recognize that lasers are fun and interesting, even though we don't yet know that we're going to use them for CD players.
So if you don't mind me elaborating, I guess so I love this, but the challenge that I think we all face as researchers is the gap between the sense that this is a good thing and the interestingness payoff can be very long. And, we know there are people who've worked decades. And so the question is, how do you modulate or calibrate that very delayed reward, especially when you don't know that the interestingness is actually connected to your final goal? Any thoughts on that?
You don't have a final goal, is my answer. You set the system off and you have it just continuously do more and more interesting things forever, and good things eventually are going to happen. You can try to create some versions of algorithms that are kind of roughly pointed in certain directions, but still you really want to not have a tight rein. You want to say, we're roughly trying to produce ever a smarter AI rather than like a better, agent that makes paintings. So work on things that you think might be roughly in roughly level us up in terms of intelligence, but don't be too myopic about it. And then you just ask a foundation model, given everything that's happened so far, is this an interestingly new thing? And you hope the foundation model has kind of distilled enough of the ineffable sense of interestingness from humans that it doesn't have to get it right every time, but it basically is kind of saying, yeah, that sounds like an interesting thing to work on. And, memorizing another 10 random digits, that doesn't sound like an interesting thing to work on. And my supposition is if we just scale that up, then really good things are going to happen.
Thanks.
I don't know if you're convinced or not.
I'm only I worked a lot in gold condition RL for robot path planning, and it's fantastic, and I love it. And yet tweaking that gold conditioning, which I know you're kind of saying we don't need the gold conditioning. My sense is if you don't have gold conditioning, the search space is too big and everything explodes in every direction in a high dimensionality space, and that scares me. And if you have gold conditioning, I think we want it, but then it gets very tweaky to make it really work well.
Yeah, so I love this debate. I think this is one of the most kind of philosophically uneasy things about my entire career and direction, is people really want to hold on to that goal. And I would just say, go back to the first slide of the talk, or whatever, the third, the cooking technology and the vacuum tubes and electricity, that sometimes if the goal is really, really hard, the only way to accomplish it is to probably let it go or very loosely keep it in mind. I'm thinking of like scientific grant agencies that want to do space exploration. They focus on some stuff. They're not going to maybe encourage you to play violin in new ways. They're going to encourage material science and maybe math and physics, but you have to be pretty loose and just kind of allow innovations to accumulate. And ultimately, over the course of decades, you'll start to make progress towards your goal. But you're right, it's not going to be, you're going to end up doing a lot of stuff that maybe isn't on the path to the goal. But with enough compute, then it's going to work out well. So this is something that's very aligned with the bitter lesson. This stuff just gets more and more powerful the more compute you have. And I think that there's enough, the interesting things are such a small subset of the overall thing that you end up, hopefully, ignoring a lot of the stuff that's truly useless, and building up a repertoire of interesting stepping stones that probably ends up doing wonderful things, including maybe accomplishing your original goal, but maybe not. Maybe it just does something else that's really interesting and it isn't your original goal. So this is not the best thing if you have only one thing only that you're trying to accomplish. It may not get you there, but it might actually be the only thing that has a shot of getting you there. So it might still be the right thing to do because your goal is ambitious and hard, and we don't have a better path to it. So yeah, that's my pitch.
Basically, my takeaway is curiosity-driven research in universities is a good thing.
That's right. And so basically, that is totally exactly right. Take that lesson that every scientist basically believes in and apply it to your own algorithms where you're not used to applying that lesson.
Yeah. Too bad the rest of the world doesn't believe us anymore on that. But that's another, yeah.
Well, and I would say you don't even believe it. You know, I'm going to point out a little bit of a contradiction just to have some fun in this talk. You believe it for science, but you don't want to believe it for your own algorithm. And so everybody, even granting agencies, you know, you talk to any any company, any granting agency. When I was at OpenAI, they're like, "What do you want to do?" I was like, "I want to do this weird thing." And it's like someone's always like, "Well, how does that what's the practical implication?" Talk to any journalist about science, like justify how that's going to make money. And it's like, no. It's just interesting, and good things are going to eventually happen. And so if we believe that for science, why don't we believe that for our algorithms? That might be the TLDR of my whole talk.
It's scale problems all the way.
Yeah.
Let somebody else talk.
All right.
Okay, and then we have, so I see Blake and Tegan raising their hands. Are the questions related to this subject?
Yeah, my question specifically related to this discussion. So if I may insert here, this is all really fascinating, and I love these questions. I want to just ask about this idea, though, of using interesting as the metric for determining this stuff, because I think it's worth noting that the examples you give of where this sort of curiosity-driven stuff has benefited the long-term technological advances we make are notable for the fact that often the most useful, we really saw sort of takeoff in terms of our ability to do things when arguably our society's concept of what was interesting changed from something that was say relevant to your religious practices or some other ancestral tradition or something like that, transformed into it's interesting if it tells us something about the world. It's interesting if we learn something about, truth, as it were, by doing this thing. And that type of curiosity-driven research was what ultimately led to this accumulation of really useful knowledge that led to totally novel solutions. Whereas, if I had gone and asked, a monk in 4th century Rome, what is an interesting thing to work on? It's possible they would have generated some stuff that wouldn't have been very useful for me. So I guess I'm wondering, to what extent do you think you're going to have to really kind of spend some time optimizing this reward function that you're using for your interesting metric for discovery here? And how have you thought about potentially doing that?
It's a great question. I think one of the benefits of having foundation models is we can kind of inherit the recent work that has worked for humanity, which is kind of to use an interestingness measure that is more akin to science and technology and modern ways of thinking. You're going to get a lot of that just because you're using a model and asking it. I think that how you prompt it is an open question. There hasn't been a lot of work into different ways to ask for different flavors of interestingness. That actually would be a great subject for a research lab or a PhD. And I think another really fascinating question, there's two related questions. One is if you wanted to specifically fine-tune a model to get better at judging interestingness, then you would have to really address the questions you're asking, which is kind of what are you going to ask it to how are you going to ask it to adapt and be even better at that task? Just based on current training data that exists online, you could fine-tune it to be really a specialist on this. But another really fascinating question is, okay, imagine that my system works and I end up innovating for a really long time. Eventually, the model of interestingness that we're at is going to get out of distribution because it's not used to all these new innovations that have happened. It was trained on, data up till 2021. So, people often ask me, like, how far can this thing generalize out into future discoveries? And my stump speech answer on this is that I actually think it's going to generalize a lot farther than people think. And the reason is because I'm not asking a model, is this artifact interesting in a vacuum? Right? I'm not saying, is the iPhone interesting? I'm always asking, is the iPhone interesting conditioned on everything that came before? It's always conditioned on the existing archive of innovations. And so, if you take a human from the 1500s and you bring them forward to the year 2020 or whatever, 2000, they're going to be blown away. But give them a couple months, they adapt, and then you say, hey, given everything that we have so far, does the iPhone count as interesting? I think they would say yes. And if you brought them forward to 2020, you repeated the experiment, and you say, given everything that we had, does a cell phone count as interesting? They would say no, because that already exists. And so just the simple task of conditioned on this set of stepping stones, is this new one interesting? That's a pretty simple function that I think will generalize far. Now, eventually it will break down, and then you have to fine tune it. So to get back to your question, how do you fine tune a model online to learn what counts as interesting given everything that's just happened? And that's really interesting. And so, for example, you could imagine that this system has to learn, hey, within the history of innovations that I have produced, which ones ultimately led to later breakthroughs? Which ones did the system build on successfully? It's almost like a test of time award for innovations within the system itself. And then you have a credit assignment problem, and maybe you can figure it out. And maybe you can bootstrap itself in that way to continuously refine a notion of interesting based on its own history of scientific discovery. This is kind of what I want to spend a lot of the rest of my career on. I think this is all fascinating stuff, and we don't have answers, and it's fun research. And honestly, the reason I give talks like the one I'm giving now is because there's 100 people online that might want to work on this and have interesting things that they want to do in their PhD or, with their lab. And so come join us on this journey. I really think it's like a wide, pun intended, open-ended field of research to figure these questions out.
Cool. Thanks.
Yeah. All right, I think I'll get back to some of the stuff that I want to share, and then we can have a really rich discussion, but there are a couple more projects I want to tell you about. So if you don't mind, I turned off my screen sharing because I wanted to see who I was talking to. Let's see if I can get back to...
It sounds good. We can keep the other questions until the end.
No, it's fine. Again, clarifying questions are... that was really fun. I think it woke everybody up, but...
okay, because I saw there are still 2 questions on the chat, and I saw Tegan also was raising her hand. Do you want to take?
Hey, Tegan, how are you?
Hey, I'm okay. How are you? Good to see you. Mine can wait till the end. It's like open-ended.
I look forward to that. Is there a clarifying one, or should I press on?
Sorry.
Tegan said she will wait till the end, so that's great. And then I was asking if the other one was clarifying or if I should just keep going.
Yeah, I think there was one clarifying question from Andre. How do you disentangle progress in Genie with respect to prettier aesthetics versus more interesting / informative environments to learn from? Or more generally, surface level diversity versus diversity in what agents can learn to solve?
Well, that was a little fast. Can you say it again?
Oh, sorry. So how do you disentangle progress in Genie with respect to prettier aesthetics versus more interesting / informative environments to learn?
Oh, I see. Yeah. Well, you just kind of hope the foundation model is smart enough to handle that. You don't want it to get distracted by eye candy. I mean, eye candy is fun too. Almost every action movie is the same basic plot with different graphics, right? And same with a lot of video games. So there's some eye candy distraction that'll happen and innovation you want, but also, you want it to kind of, hopefully once in a while, it comes up with a new genre of games or a new genre of challenges, and it recognizes that also. And hopefully the model is good enough at picking that up. And with scale, even if it's wrong half the time, that means it's right half the time. And so half your stuff is really good. And we'll take that. I want to remind everybody, most algorithms, when you run them, they run out of steam very quickly. At the beginning of my career in grad school, there was no algorithm that existed that was worth running for more than a few hours. And then eventually we get algorithms that are worth running like a day. And then with things like AlphaGo, we have algorithms that are worth running a few months, maybe longer, but they're still narrow and constrained to a specific domain. And the goal here is to create algorithms that you could run for 1 billion years. So even if it's not perfectly efficient, as long as it's doing something interesting with 5% of its compute, that's pretty interesting because you could run it for a really long time and wonderful things will happen. And that's exciting to me. So it doesn't have to be perfect. All right, I'm going to keep going, share some more stuff, and then we can talk more. So this work here, Automated Design of Agentic Systems, led by Shinran and Song out of my lab here. First, I'll just introduce some terminology. So LLMs typically were, a prompt, you give it some words, it runs it through a neural net, it gives you back some text. Nowadays, almost everything we interact with is what we call an agentic system, which is a foundation model that's a core inside of a much more complicated workflow. It's like a flow chart. It might make a web query, it might read the results of the query and then have an LLM summarize them. It might have an external safety LLM that's checking whether or not the response is racist or biased. It might actually think really hard. It might create a debate amongst 5 copies of itself and then have an area chair, like, figure out which of those proposals is the best, etc. So there's these complicated flow charts like reflection, chain of thought, whatever, and they improve performance a lot. But if you look at them, they're all 1, hand-coded, and 2, quite complicated. So you can kind of take the lesson of the AI generating algorithms paper and say, hey, we know hand design efforts will get replaced by learned efforts with more compute and data. So let's just use machine learning to find and discover better agentic systems instead of trying to hand design them. And so let's also bring in the open-endedness principles. Let's grow an archive of interestingly different agentic systems, pull one out, try to improve it if it's interestingly different or the highest performance version of that type of agentic system, swap it into the archive, grow your archive of stepping stones, do it forever. And so we're going to create we're going to search for agentic systems in Python code that's Turing complete. Therefore, it can create any type of agentic system. And then we're going to grow this open-ended archive of agentic systems using the basic playbook. And what we show is that this works quite well. So here's on the ARC challenge, you start off with a pretty terrible performance, but slowly but surely, as you give it more compute, it comes up with better and better designs and ultimately outperforms a lot of the state-of-the-art hand-designed agentic systems. Here's an example of the best one it found on this challenge for this domain. It gets quite complicated, but the ideas are quite intuitive and will generalize to other domains. And we showed that. You can use this on different domains like math and reasoning. You can also take an agentic system that was designed for one math or reasoning task and transfer it to other math or reasoning tasks, including like a math agent ends up being good at reasoning because it's coming up with general principles that are pretty powerful and useful within an agentic system, like check your work or have a debate amongst three proposals and have 5 experts judge those 3 proposals and like use majority rules or whatever. So you get a lot of transferability. So ADAS was pretty cool, but we wanted to then allow ADAS to improve itself. We call this the Darwin Gödel Machine. And that's because Schmidhuber in the early 2000s, I proposed a Gödel machine, which is something that is like AI that looks at itself, and if and only if it can come up with a proof, a mathematical proof that a change to its own code would improve it, then it takes that step. However, in practice, that's impossible. You can't prove that a change is not beneficial for any complicated AI agent or task. And so the Darwin Gödel machine says, hey, we're going to abandon the requirement to prove that you're improving yourself. We're just going to ask you to come up with some evidence that you've empirically improved yourself by running some experiments. And also we're going to use the open-endedness playbook. So we're going to grow an archive of different agentic systems. They can change themselves, including improve themselves, which makes them better at the next change to improve themselves. And we show that this also works. So here's a phylogenetic tree of Darwin Gödel machines. And what's really cool, you can look here on the right, is that oftentimes the path to the best eventual agent had to go through local optima. It got worse before it got better. It wasn't obvious that this innovation here would ultimately produce the best agent. And so we show scientifically that if you don't allow the agent to do open-ended, like grow an archive of interestingly different stepping stones, that's orange. On 2 different domains, that works terribly. And also, if we don't allow the system to improve itself, then you don't get better at improving yourself and then better at improving yourself. And that also doesn't work as well. So really, it was a combination of these 2 different principles of self-improvement and open-endedness that ultimately produced blue, which is better than the alternatives. So I want to just emphasize that we really cared a lot about safety for this work. We use containerization. We hand monitored the system to make sure it wasn't making some evil genius version of itself. But a lot more work is needed to make this stuff safe, because I guarantee you the field is going to continue to work on self-improving AI. I consider that inevitable, which is a controversial take. But given that, I think we need to make sure we do a lot of research into how to make such exploration safe, including like having the system have a sense of ethics and not want to do unethical research, unethical improvements. And so I've written some articles about that, and I want to work more on that in the future. So yeah, actually, I think I'll just skip that. So and the next thing I want to tell you about, there's two more that I want to tell you about, is the AI scientist. This is trying to fully automate scientific discovery. We're done with these wonderful people. And the idea is that science is the ultimate open-ended domain. Obviously, there's lots left to be discovered in the universe. And so can we have AI automate all of science? And what we show in this paper is a proof of concept that yes, we can. So we chose machine learning science because the computer is the real world. There's no like external world we have to worry about. You could apply the same ideas to automated labs if you had like an automated chemistry lab, for example. You'd really want to get safety right if you were doing that. But the AI scientist, it generates ideas, it designs and runs its own experiments, it analyzes and visualizes the results, including making plots. It writes the entire scientific manuscript from the first word of the title to the last period in the references. It conducts its own peer review to try to figure out if the work is high quality and interesting. And if so, currently it returns it to us, the user, and then we do something with it. But in the future, I want it to publish that to an internal archive of papers, read those papers, produce the next paper and the next paper, and really automate like a community of machine learning scientists, have its own NeurIPS, et cetera. Interestingly, we saw some examples where we saw the system produce an idea, and then a couple of months later on Twitter, some human group of scientists did that idea, published it, and the community celebrated it. And so this thing is capable of being creative and coming up with new ideas that no one had thought of before. It also produced an entire paper, actually produced 30 papers. We manually chose the top 3, submitted them with permission of the organizers to a workshop at iClear, and one of them got accepted for peer review. So this at a workshop. So this has already survived peer review. It was in the 55th percentile. So it did better than 55% of the human scientific teams that submitted to that workshop. And this is currently in review at Nature. So if you're a fan of the work, then wish us luck. If not, then the opposite of that. So again, we're really interested in the safety and the ethics here. We were real sure to containerize everything. We believe in full transparency and always telling people what's AI generated. So we watermark the heck out of things. And again, like we don't want this system to go and do gain of function research on COVID or, like horrible science like the Nazis did on twins. So we need this system to have a sense of ethics in terms of what kind of science is okay to pursue and what kind isn't. And that is a really wide open area of research that I'm interested in, and I hope that other people will join me in. So future work here, as I mentioned, there's so much you could do, different domains, scale it up, whatever. But the one that I'm really excited about is here in yellow, when the system starts to build on its own discoveries in an open-ended way, and then we have a true open-ended algorithm. All right, the final bit of work I want to tell you about, and then we can have a discussion, is ACD, Automated Capability Discovery. Here, we basically wanted to say, hey, let's not just try to do open-endedness and be safe about it. Let's use open-endedness for AI safety to try to improve the overall safety and alignment of everything that the community is doing. So here what we want to do is use open-ended algorithms to basically try to identify ahead of time for a given new frontier model. We'd like to know before it's deployed, does it have surprising new capabilities that might be dangerous? And does it have surprising new failure modes that might cause it to be racist or sexist or, attackable and usable for something evil? And so right now, typically there's a big red team within an org like OpenAI. They have to do their best, but they're just a small team of people. Relatively slow, and they can't figure out everything that the model can and can't do. And then we deploy it, and the crowd kind of figures out what it can and cannot do. And that is not really when you want to be figuring out that it has some dangerous new capability. So here we just say, can we basically we're going to have a scientist model. This is a frontier model that's going to be studying some other new model, which is the subject model. And the scientist model is trying to iteratively poke at the model and figure out, are there surprising new capabilities and failure modes in the model? And then we're going to grow an archive of interesting discoveries. Because once you discover that it can't can't count the number of R's in strawberry, you might figure out, can it count this, or can it count that, or can it do the same thing in other domains. And so you kind of learn, use past discoveries of interesting surprise success modes and failure modes to then think of the next experiment to try and the next thing to try. And you iteratively grow this kind of archive of discoveries about a model. And then you could turn around and serve that up as a report back to whoever made the model, or maybe to an AI safety institute, to say, hey, here is kind of like all the fingerprint or the dashboard that tells you about this new model. Now, it won't have discovered everything, but it might tell you a lot about your model in an automated way and come up with discoveries that your human red team did not come up with. So that's ACD. Okay, I mentioned this playbook is very general and powerful. I've told you about 4 examples of it with foundation models. There's a couple more that are here in green that came out of my lab that I don't have time to tell you about, but you can check out those papers if you want. I want to conclude with this thought. These algorithms, if you're not that impressed with them, I just want to remind you, this is the worst they will ever be. You know, I just keep going back to this picture. I think everyone should like print this out and put that on their wall or their phone or whatever. In 2014, this was AI generated faces. And in 2024, this is AI generated faces. You could do the same with Genie 1 to Genie 3. All of this stuff, once it becomes somewhat possible to do it, it's not too far before it's really, really, really powerful. And so you can apply that to the AI scientist, you can apply it to Genie, you can apply it to ACD, all of these different things, OMNI Epic, etc. All of this is going to get really good really soon. And we just need to reckon with that as a community and try to make it as safe as possible. So 3 conclusion slides, and then we can chat. Quality diversity algorithms are these things that explore really well. They create and collect stepping stones. They harness goal switching in these weird counterintuitive curricula. Open-endedness is trying to create things that endlessly learn and innovate forever, like evolution and human culture. And AI generating algorithms is basically harnessing these ideas to produce AGI or ASI. I think it's the fastest path to get there. OMNI allows us to finally pursue what's interesting in Darwin complete search spaces, like code or foundation world models like OMNI, Epic, and Genie. VPT and SIMA and pre-training allows us to kind of like skip past the early learning stages to kind of the interesting part. If you think about it, evolution took 3.5 billion years to produce a brain, and then look at what you to produce humans, and then look at what you have done in the last 100 to 200,000 years as a civilization. It's really remarkable. So pre-training kind of allows us to skip to the interesting part and have sample efficiency woven into these open-ended systems. And that I just think this playbook is really powerful. Like, think of all the different things you can do if you grow an archive of interestingly different stepping stones and you harness foundation models to do that. I've shown a lot of examples. There's many, many more to come, and maybe people on this call will use this playbook and innovate and create the next 5 things on this bullet list. So I want to leave you with this thought. I think that open-endedness and AIJs are the next wave in AI. That's a bold statement, but it feels like yet another scaling paradigm that can benefit from infinite compute and really do wonderful, powerful things. Obviously, we want to make that safe, which is important. But I would just leave you with this thought: like, what else can we create? Can you create in your world with the domain that you care about with this playbook and these set of ideas? So with that, thank you very much, and I'm happy to take questions.
All right, thank you so much for the amazing talk, Jeff. Yeah, so I think there was first Tegan and then Mandana, and yeah, go ahead, Tegan.
Yeah, okay, so I actually won't ask the question that I was going to ask then, because it's a bit more open, and I'll give other people a chance. Thanks for the talk, as usual. And in the interest of brevity, I'm going to, say this or ask this question in a little bit of a playfully hostile way. So just for people or friends. I know it's fine with you. I'm just saying it, I guess, for everyone else. I'm not just being hostile. So what you just said in the last part with the AI generating agents, about choosing machine learning as a domain because it's 100% code. That is a maybe Darwin complete or Turing complete environment by itself. I think that's completely wrong and ridiculous, and in a way that is very the whole AI community tends to jump to that. And what I think is very wrong about it is that anything that is interesting or useful about the scientific ideas that come out of the AI scientist, for instance, is grounded in the real world. It's stuff that is real. Like a machine learning algorithm doesn't make sense except as something that improves that experience on a task that is defined in the real world with data and experience that is defined, that it comes from the real world. And I think eliding that connection to the real world and not being explicit about the ways that what we parameterize or encode for agents and data, how those things tie back to the real world, I think that makes safety impossible. If we don't have really explicit ways that we say what is true and what is real, what is coming from a real source versus what is hallucinated or what is like an artifact of the optimization or search process or whatever, I think that makes safety impossible. So I think we have to be very explicit about where and how we are connected to the real world through the task design, the data, etc. I guess this is more of a rant than a comment, but I'm sure you have thoughts about that.
Yeah, so I think that I didn't mean to imply that just because you're doing machine learning as a domain that you are disconnected from the real world. For example, if you are doing well on ImageNet, those images ultimately are pictures of the real world. They're not synthetically generated pictures. What I meant to say there is that in machine learning, once you get a result in silico in a computer, you're done. You have shown a better method. So if, for example, I can train on ImageNet and get state-of-the-art performance in 3 seconds, for example, I don't need to be like, it's not like in biology where it's like, oh, I have a simulation of whether these two proteins bind and I found a protein that binds really strongly, but now I need to go check the real world to see whether the simulator, I hacked the simulator in a way that's actually not real. And the real test of success is ultimately out in some other world, and I have to deal with what's called the reality simulator gap. In machine learning, that's not true. Like if I can train.
It is true if you care about safety and ethics and how you impact the real world with your machine learning technology is not expressed in like an ImageNet benchmark. Yeah,
fair enough. For example, I could produce perfect performance on ImageNet and it could be wildly overfit. And in the real world, the image detector sucks. I agree with that. For the most part, though, you can do a lot of your experiments in machine learning on benchmarks in a computer, and that counts as a full stop. Like I made a better algorithm. It is true that ultimately we do want, and people did with ImageNet, they figured out, oh, well, my gosh, these things are actually, like does ImageNet generalized ImageNet? It's one of my favorite papers. And we do as a community need to also do that. So I don't really mean to imply that the system itself could only operate forever in a computer and we would not care about the real world. I do mean to say, though, that it's the low-hanging fruit for AI science because you don't also have to deal with like wet lab experiments. That's all I meant there. Now, to your broader point, I think one of the things you're touching on is synthetic data. Can we train on it? Does it become ungrounded and divorced from the real world? I totally do think that we, for any system to help us and make humanity better, it periodically needs to ground itself in the real world. And that's going to be conducting real experiments, seeing how these algorithms and these things that we've made like work in the real world. And so actually the long-term future here, even for ML science, is to periodically be checking for whether or not you're doing something that's helpful for humans in the real world. So I fully agree with that.
Yeah, I think if it's only periodic, you're not going to have the ethical mindset that you're talking about, but I'll leave it to other questions. Well,
I'll just, I'll counter that. If I had, for example, if I had a system that was learning a better system, a simulator of like cells, and it within the simulation of the cell that it had learned, it did a million experiments and found what it thought was a really good innovation, and then periodically checked that against the world, found that that isn't actually real, this because the simulator of the cell is broken, got some data, improved the simulator of the cell, went back and hit the simulator of the cell for a while in simulation, and then periodically like went, it's the kind of iterating between the simulation and then updating the simulation and whatever. That's a healthy loop, and you don't have to have every single experiment be in the real world. You can use learned proxies and then ground the proxies by periodically updating them. Something like that feels really healthy to me, and I think is totally aligned with safety. As long as you do it, other things right. Like you don't want to be like testing out gain of function research is what you're trying to accomplish.
Yeah, I guess what I agree with you. Like, I'm not saying everything has to be in the real world at all times. It's more like if you're only checking in with your ethical compass every 10,000 iterations and not embedding that into the way the search space is designed, for instance, or whatever, then you're like embedding kind of Machiavellian thinking at a high level. I think there are totally domain science experiments that can proceed entirely safely in an open loop like you're describing.
Yeah, I would be happy to check the ethical compass every single time, even in simulation. That's like a separate conversation. You might not need to do it, but I'm totally happy to do that. Getting ethics to be woven into like everything that we do all the time, as opposed to something we think about like at the end of a project, is something I'm fully on board with and want to do more of.
Okay, and then we have a question from Mandana. Yeah, I will just read your question, Mandana. In the OMNI paper, interestingness is defined in terms of deviation from the agent's expectations about the world dynamics, but some of the most important discoveries in science or evolution aren't immediately interesting or don't yield learning progress until much later. How do you see OMNI or future extensions of it addressing this gap between optimizing for short-term interestingness and enabling the discovery of long-term discoveries whose value isn't immediately measurable?
Yeah, I mean, I don't know. I'm actually going to push back. I mean, it's not that often that we make an innovation in science that somebody didn't think was interesting when it happened. I mean, that's why they chose to tell somebody else about it, right? Like, somebody looked at some mold in a petri dish and was like, that's weird. I left the mold for a week and this thing doesn't have mold growing in it. Why? And then they started to study it and we get penicillin. In fact, probably some of the big misses in science are when somebody saw something happen and they didn't recognize that it was interesting. But usually what happens is somebody says it's interesting. Now, it might not be earth-shattering, right? It might just be like, that's funny, or like, that's interesting enough that I'm going to like write down my observations and write a little paper or a blog post, or even just like share them with a friend. And then maybe later in hindsight, somebody's like, that was a key moment and we figured it out. So there's kind of like this tension here. It's like, is it like interesting enough to share versus like, do I recognize that this is going to be the breakthrough that ultimately leads to whatever? So I totally agree with you. We don't often recognize that this thing here is going to end up being a major breakthrough. But all we need to do is say that's interestingly different than anything else. And so I want to write it up and put it into my little archive of growing knowledge. That's a pretty low bar. And as long as we do that, then we probably have enough fuel. And we don't have to get it right every time. Humans miss interesting stuff all the time. But as long as we catch some decent fraction, then we'll grow a reservoir of a really interesting stepping stone so we can leverage, just like human science communities do.
Okay, so I just want to clarify. Yeah, thanks. Actually, that answers the question. But I was thinking more like, what are the notion of, how could you measure interestingness in the long term? Like, because I feel, so I really liked OMNI paper, but there, so we are relying that the language model is able to say, this is an interesting, environment to explore. But this is really maybe just based on the current training data, and we don't really know if this is going to be long-term, whether this is going to have any impact in terms of scientific discovery or not. So I guess my question is that, what are your insights on measuring this type of interestingness more in the long term rather than what we know today?
Yeah, so I kind of gave my answer to this question earlier. Okay. I'll try to summarize it. Two things. One is I think it might generalize much farther than we think, because it's always asking, not is this interesting in a vacuum, but is this interesting given everything that came before? So imagine, for example, think of this thought experiment. I'd take you forward 100 years. And so to the year 2125. When you get there, you're super surprised and blown away by all the new technology. I hope we're still around. But after you've had a month or two to acclimate, my guess is that I could ask you, hey, here's what we've got so far. Somebody just proposed this. Is this interesting? And you would be able to do it because it's all conditioned on the archive. Now, ultimately, if there's like wildly new types of math or language or art or whatever, you might not have the features to kind of think about and process that new math and science. And so I might be able to give you 10 ultraviolet operas. I just made that up. And you can't recognize whether the 11th is interesting because you don't know how to like think about, you have no features to recognize what's interesting within the first 10. So ultimately you will have to fine tune and update. Now there's two ideas here. One, you could just do generative pre-training on everything you've generated so far, just next token prediction on the archive. Maybe that allows you to start recognizing the beauty and the interestingness of 10 ultraviolet operas. But also you could start to do like that test of time thing that I was talking about, like within the community of discoveries, this ultraviolet opera has like many people have like built off of that. And that led to other things that we thought were interesting. This other one, or this scientific insight here, this paper that was published within this community of AI scientist papers within the archive. Every time people build on this technique, it's a dead end. Every time people build on this dead end, this technique, it works a lot and there's a lot of innovation. So maybe after like a lot of growing discoveries in this archive, you can look back and kind of figure out which ones were interesting and more powerful than others. And that can allow you to update your interestingness function on the fly as you go. Who knows if that'll work? And there's probably other ideas that you guys are having that I haven't thought of. And so I think this is actually one of the frontiers of research in this field. And it's really, really exciting to figure out how can you do online updates to the model of interestingness that stay grounded and don't just kind of end up like, you know, fooling themselves, like Tegan was saying. You don't want to become untethered from the real world.
Thank you.
Yeah.
Okay, so we still have like 4 questions, and I see that we are already on time. So, Jeff, do you mind sticking around?
Yeah, I'm happy to stay. Sorry, my talk ended up to being long.
No worries at all. So for people, for people who want to ask their questions, we can have 5 more minutes. So let's start with Maximilian. Related to safety, do you have any worries that optimizing for interestingness could be too hard to align with optimizing for our well-being? If not, how do you see the two naturally connect?
Great question. Great question. Yeah, my instinct here is that, and first of all, this is just a wide open area of research. We need so much thought into this. So I am not going to give you the answer. I'm just going to give you my current thinking. But we need a diverse set of minds working on this problem. I somewhat feel that the way to do this is probably to have an ethicist AI watching the system that is not simultaneously also being asked to do things like maximize learning and maximize interestingness. Like, I don't want multiple objectives in the AI, the kind of the ethical police, the ethical compass. I think we probably want the system to be proposing interesting ideas and useful ideas and learnable ideas. And then this separate ethical thing, its job is basically to just kind of watch and say, no, we're not going in that direction. Like, you're getting like an ethics red flag, you're getting blocked from going there. Now, it's probably even better if these original pieces also have ethics, so they don't even propose and want to do certain unethical things. But instead, I think that at a minimum, at least one ethical agent should only care about ethics and nothing else, because I don't want it making trade-offs between interestingness and safety. Like, at some point, there were scientists who were like, wow, wouldn't it be really interesting if we did this experiment, that experiment? And they didn't have enough ethics. And so we ended up doing like horrible research on twins in Nazi Germany, or maybe like dangerous gain of function work on COVID, or whatever it is you think is something that scientists shouldn't touch. And so I guess maybe the answer to balancing it properly is to not try to balance it at all and make ethics the first class citizen that doesn't get overridden by other concerns.
Thank you. Okay, and then I think there was Tegan after, and then Adam.
Yeah, thanks. It's again a little bit of a like pushback, or what do you think about this pushback about scaling and compute? So I think we often use those as proxies for time. And I don't think they always are good proxies for time. Like, what you want is to run it for 1 billion years, if you said it, or something that would be interesting if we kept running it for 1 billion years. And we could do that with less and less compute over time. So this sort of connects to like arguments about making AI more energy efficient, and maybe the observation that the natural world is like energy efficiency is a very strong selection pressure. So maybe I'll just throw that out there as the cloud of question.
Yeah, so 2 thoughts. One, I think will be uncontroversial, which, well, 2 two thoughts. One, of course, we want things to be more efficient. But for me, the reason I want it to be more efficient is because I want to see further. Like I want science to progress faster and the algorithms to be able to go even longer. Like now that we have algorithms that we might want to run for a really long time, I want to make them more efficient so I can actually run them and see where they go. Because if you have an innovation engine in a bottle, like don't you want to see what it comes up with? Like I want to watch OMNI and see what crazy worlds it comes up with, or I want to watch science proceed faster so we can cure cancer. Like I don't want to die.
Right, but you're talking about that as a like efficiency is a secondary concern. It's like we'll in the inefficient space come up with solutions and then make those solutions like in an engineering way more efficient. But if efficiency is kind of like ethics, maybe not first class, but like let's just say first class selection pressure, you'll come up with different solutions than you would if it wasn't.
Yeah, that's true. You could, I mean, the system for sure, an AI scientist system would be silly to not try to make everything more efficient as it goes and come up with innovations that make things more efficient. And so that's great. I think to the general, I'll just say something pretty controversial because it's always fun to mix it up in these kind of discussions. A lot of people are concerned about like the environmental impacts of these kind of algorithms. I kind of thought of an analogy just now. Like if you went back to like, I don't know, the 1800s, you know, like, hey, telescopes take a lot of telescopes and microscopes take a lot of resources to make. Are we worried about like the environmental cost of telescopes and microscopes? I'd say like, no, scientific discovery is really exciting and I want more telescopes and microscopes. I'd much rather make fewer bombs and like invest a lot less of society's resource into all these other crazy things that we do that are wasteful. Like this is not the place we want to be like really, really frugal. Because who doesn't want to see like, you know, leukemia solved? And so I think that if we can automate scientific discovery, then we can really do some wonderful things for humanity. And like, let's look for other places to like cut back on like waste. So I'm personally not as concerned about spending energy on AI. I'm not going to endorse Sora. That's maybe not the best use of it, but AI science, yeah, sure, I'm all for that.
Yeah, I think that comment from academics just gets taken out of context a lot of the time to justify, you know, selling us more ads, basically.
Yeah, we want to be. I mean, I'm not about the ad thing, and I don't want, you know.
No,
So, and I know you know that, but for everybody else on the call, you know, like we want to do wonderful things with this stuff, but I don't want to put a chill on expensive algorithms because all expensive algorithms bad. So we want to be a little bit more nuanced in where we're thinking of in that way.
Okay, and then there was Adam.
Hey, Jeff, thanks for the talk. I see a lot of people asking about the fact that we cannot know in advance whether something will end up being interesting because it seems not so interesting in the moment, and maybe a long time later we find out that it could have been, you know, a stepping stone for something more useful, etc. So I feel like what I'm going to ask is obvious and probably exists in the literature, but this to me sounds very much like what we mathematically captured in regret and the likes. And so can't you at a meta level consider like regret as a way to capture this, the fact that you do not know necessarily, but you can estimate, you know, same as with Q values, you can estimate how this will add up to some measure of regret. The fact that you might have missed a long time in the past, something that will end up being useful, etc.
What a great question. You made me have an idea just now that could be a good idea. I'm not sure. Almost every idea when I first have it, seems great, and then I figure out later why it's not great. So I'll say it out loud, and then you guys can all think about all the reasons why it's not great. But you could imagine trying to create a version of one of these open-ended algorithms where it is trying to figure out some counterfactual thing, like maybe every time that I go to produce a new building block, sometimes I condition on A, A being a stepping stone in the archive. Sometimes I don't. And do I, on balance, come up with better innovations when I condition on A versus not? Maybe that's a way to figure out whether or not A was interesting and useful, and some regret notion with respect to A. And then you could apply that to every stepping stone. And so you know, like the ultimate super expensive thing is I create one archive with A, one archive without A, and then I go and I see like which one does better, but that's way too expensive. But maybe some sort of kind of like just masking out to do credit assignment for how good A is could give you a sense of whether or not A is useful or not, which I think is related to your concept of trying to figure out whether or not we have regret for including A or not including A. And I just want to push back again on the original assumption of the question. I don't, like, we humans all the time, we have to make judgments of whether or not something's interesting. And we're not perfect at it, but the system itself can, I think, probably do a decent job of recognizing like, hey, that's weird, that's new, I've never heard of that kind of an algorithm or a problem, and it kind of works. It has signs of life, so you know, let's keep it. Like, this is not that hard of a challenge. We do it all the time, and we don't have to be perfect at it. And as long as we kind of get it right, that might be the rocket fuel that allows us to create these algorithms.
Yeah, although you could consider that maybe, like through evolution, there is a diversity in the way people think that could be more pronounced than what current models get as diversity, because of the fact that we tend to use the same data sets, and that this individual diversity in humans, when they become researchers, etc., leads to more diversity of exploration.
Yeah, so you're like an idea generating machine over there. So now imagine taking that idea, and somebody could do a paper or a PhD on what you just said. So don't use one model in OMNI to judge if things are interesting via different prompts or fine-tuning different models. Have a diverse set of minds judging interestingness, and maybe you only have to convince one or a few of the people that this is interesting, and that goes in the archive. And by having wildly different MOIs, which is models of interestingness, maybe we get a better result than just having the one. That's a really exciting area. Somebody could do papers on that. That probably would work better, honestly. Nice job.
Okay, so we are already like 11 minutes over time, but there are two people who want to ask their questions. Jeff, do you want people to maybe email you, or do you want to continue the discussion? Like, it's
I can try to answer the questions now. I think that's better than email, and I know that people might have to drop off. So why don't we take those two, if that's what you said there are, and then we'll conclude.
Okay, sounds good. So the first is from Sam. Sam, do you want to unmute yourself and like say your question? I think it would be easier.
Yep. Hi, Jeff. Hi, good to see you again. Yeah, fantastic talk. I'll be quick. If the fundamental drive isn't for novelty but algorithmic utility, maybe discovering building blocks that maximally compress the solutions to widest range of future problems. I mean, have you thought about this? Maybe this is a way to actually improve the notion of interestingness, to actually get beyond just, say, pre-trained human notions of interestingness, to maybe kind of use an information theory point of view to then scale it up. And I have ideas how we could do that.
Yeah, it's a good question. I mean, people should try this. I love compression. I've like read all the old Schmidt-Huber papers, and they seem great. But in my experience, every time you try to use that stuff, you end up with like crazy pathologies and nothing works. So I'm not that bullish on figuring out. To me, that's kind of like the old school way we used to try it, is we'd come up with some information theoretic measure of interestingness, and it related to compression or prediction or whatever, and then it just doesn't actually work in practice. So if somebody could like resurrect that and make it work, great, we should play with it. But I'm not that bullish. I'm more bullish on just like train a model on the internet and then like ask it.
Great, thank you. That's really helpful.
Yeah.
Okay, and then last question from Andre. Andre, do you want to unmute yourself?
Yeah, hi, can you hear me?
Yep.
Hey, thanks for the great talk. I had a question about some of the ideas you mentioned, which is this sort of notion of conditioning on previous innovations that sort of calibrate what is an interesting innovation moving forward. You talked about history of science a bit, and there's this kind of like idea that science advances one retirement at a time, where like maybe the body of ideas that are like currently the zeitgeist are actually hindering progress by sort of limiting the scope of what we consider as interesting or realistic.
Yeah.
like, you see this all over history of science. Like the editing experiment is one thing that comes to mind. So I'm curious if you have any thoughts about like reconciling this potential bias of conditioning on previous innovations while still allowing for like new explorations outside of that.
Yeah, it's a great question. Actually, I'll go to what Adam, he didn't propose it, but he caused me to propose it. You could imagine, well, actually, you know, he was suggesting we should probably have a diversity in human minds. So just you could have a diversity in AI minds as well. And maybe you don't need to convince 5 reviewers in an area chair to get your idea through. Maybe that's where ideas are getting hurt. Maybe you just have to convince 1. And then this gets back to the original discussion for the original question that I got asked, which is like, it's a kind of like an issue of efficiency. You could say, as long as 1 other reviewer thinks your paper is good, it gets published. Then we just have more papers. And then when you're reading through the papers, you get probably more garbage, but maybe you have some gems that would have otherwise gotten filtered out. So this is kind of a balancing act, just like it is with human science. And so you could maybe have diverse reviewers and lower criteria for being stringent, but then you have more maybe noise. And so that's probably an empirical question, like what is the right balance there and how do we strike it in a way that we can make algorithms that can go do interesting things somewhat efficiently. And this is just something we'll have to research and figure out empirically.
This kind of relates back to your point about Genie and this idea that like if you have large enough models, if like only 5% of is interesting, that's good enough.
Yep.
So I guess, do you see sort of like this idea of scaling and parallelizing the amount of things that are doing the same thing in parallel but differently? You see that as like a fundamental scaling dimension moving forward with its own like intrinsic properties?
Well, like you could imagine, if you have infinite compute, then you definitely don't want to have to convince all the reviewers, right? You just like throw it all in there. But at some point, you don't want to throw everything in there because then you're not doing any filtering. And so it's like kind of inevitably going to be a balancing act. But yeah, the more you can scale, the more you can allow a diverse number of papers to be published, basically. And maybe that ultimately ends up working better. But even then, maybe you'd rather just spend that massive compute on a smaller subset of papers. I don't have any. This honestly, if people who study the history of science might have a lot to contribute to these algorithms and like help us figure out like what is the right way to strike that balance.
Cool, thank you.
All right, let's thank again Jeff for the talk and for sticking around for the discussion. And see you all. Sorry, go ahead again.
No, I was waving at Jeff. Thanks, though.
Nice to see you, everybody, and Tegan in particular. I haven't seen you in a while. Thanks for all the wonderful questions, and it's been really fun. I appreciate it. Thanks for organizing, Lena.
Thank you.
Yeah, thanks.
Well, thank you. Have a good day. Bye-bye.